In the first 5 lessons, I gave you an introduction to atomic force microscopy. Now we're at lesson 6, and it's time to get into some details. And one of the most important set of details is that having to do with the feedback circuit. So from the photodiode, we get a signal representing the force acting on the cantilever between the tip and the sample, and we subtract that signal from a set point voltage. The set point voltage corresponds to the force that we want to hold constant as we're taking a constant force image. When we subtract those two signals, we get what is called the error signal. The error signal is 0 when the photodiode signal equals the set point signal. That error signal plus a control that's called the gain undergo a mathematical operation where the gain is divided by a time constant. The error signal is integrated over time, and the output of that operation, which is done by operational amplifiers in an electronic circuit, the output goes in 2 directions. One direction is to your computer, so that you have an image of the Z position of the scanner as a function of X and Y. And the other part of that signal first passes through a high voltage amplifier and then goes up to the scanner and causes the scanner and the cantilever to move up and down. The voltages involved here are, for the most part, plus or minus 10 volts for all of this circuitry. And in order to run a scanner, you typically need higher voltages. So a typical value might be plus or minus 150 volts, but it depends on your instrument. And what do we control here? We control 2 of these functions. We control the set point voltage, meaning what will be the force that we want between the tip and the sample, and we control the gain. And the gain has the function of multiplying that operation, and the higher the gain, the more quickly and the more response we get in Z. This whole system is called the feedback loop because, as you see, it is a loop. The cantilever sends a signal to the photodiode sends a signal to the electronic circuit sends a signal to the high voltage amplifier, which in turn sends a signal to the scanner, which in turn moves the cantilever. Let's take a closer look at that scary mathematical function, the gain over time constant, the integral of the error signal with respect to time. Let's see how that plays out in an example. The example we'll use is the cross-section of a square step, and we'll have our cantilever and it'll be moving left to right. And we'll also plot the error signal as a function of time and the Z signal as a function of time. I'll add vertical dashed lines to indicate that these 3 plots are aligned. And so what happens is, if we assume that the photodiode voltage is equal to the set point voltage when we start off, and that the scanner is in the middle of its range at 0, it can go up and down, positive and negative, then when photodiode signal equals set point signal, the error is 0, nothing happens. When the cantilever reaches an upward step, that becomes non-zero and keeps rising until the scanning system has had time to react, and after it reacts, it starts to fall, such that on the top of the step, the error signal is once again 0. When we have the downward step, the opposite happens, and the error signal goes in the opposite direction, and then flattens out when once again photodiode signal equals set point signal. What happens in Z? We say Z starts off at 0. Nothing's happening with the error signal with that nasty equation, so nothing happens. And then when the error signal starts to change, what that operation is doing is essentially taking the area of this error signal, and that area will correspond to the height change of the scanner. Then we get up to the top of the step, and nothing's happening with the error signal, so nothing happens with Z. And then over here, we look at the area of the error signal, and now it's negative, and if you remember from calculus, there are things called negative areas, and the way I tried to draw it was that those two areas had the same magnitude, and so that means the scanner would return to its original position. How do you set the feedback loop? Well, let's take another look at our cross-section, square, and a cantilever moving left to right. If the feedback loop is set too low, the gain, you get a cross-section that looks like this. So here the feedback loop is responding too slowly to give you a good representation of the surface. If you set the gain too high, what happens is the Z scanner overshoots and you get oscillations. The best you can do is to have just a little bit of overshoot. It's unfortunate but true that you can never set a feedback circuit exactly perfectly. There's always a little bit of error, and the reason is you need to have a change in error signal in order to give you a change in the Z scanner. There are two main methods of setting the gain. One is to turn up the gain until the system starts to oscillate, then slowly turn it down until the oscillations just go away. The second is to bracket the gain, and if you've been involved in photography, you might know this word. What it means is if you've got a special subject you want a really good picture of, you take a bunch of different pictures at different camera settings, and you start, say, with the f-stop too low. You know it's going to be too low, and then you systematically go up in f-stop until you know the f-stop is too high. I'll give you an example. On the left, we have a topographic image of the exfoliated aluminum surface of a CD. Those light spots are the bits representing the ones and zeros that make up your music. It's a 10 by 10 micron scan with a 250 micron color range. If you look closely at the top, you might see some little gyrations there, some oscillations. That means the gain is too high. Down here at the bottom, there is definite streaking going on. That means the gain was too low. You can actually see this information better in the error signal image. So many instruments will allow you to plot not only the topography, but also other kinds of information. So on the right here, we have error signal as a function of position over the sample. And you see in this top area, there's a lot of variation, a lot of oscillations. here in the next quarter of the image down. So I was changing the gain as I was acquiring the image. There's a little bit of oscillation. Here, this area looks pretty good. And here, we're getting a lot of contrast. Now, an error signal image, you want as little contrast as possible. That means you're making the feedback circuit work as well as it can. So the values for gain that I used were 3.5 here, 2.5 here, 1.5 here, and 0.5 here. So based on this, I would choose a gain setting of 1.5. But gain depends very much on the sample and the cantilever and your scanner and how fast you're going and the set point and so forth. So don't take this number of 1.5 as being universally applicable to all instruments, and it's certainly not applicable to all samples. With this information about feedback, I hope you can now find an AFM you can go work on and try playing with the gain settings yourself.